Hello, everyone, and welcome to this short presentation, this short webinar related to Tapered section modeling analysis using S-Frame. My name is Alejandro Lopez, and I'm the one who's been leading this short event. So since we don't have too much time, I'm going to try to cover the most important things related to this topic. So we're having or sticking to these general considerations for Tapered sections. So it's very important to have in mind a couple of things, and that is one, that the model or the Tapered section modeling lets you to model a member with different cross sections at the start and at nodes. This tapering is considered linear, so we are not adding some other shapes at the middle of the member or near the end or something like that. The other part is that S-frame averages the section properties. That means that basically takes the average point, so you may not have the most detailed information unless you detail a bit more about that modeling. And that's something that we are going to show during this short lecture. This tapering can be defined graphically or numerically. So you have two different options in case you are more inclined to work with one or another. And lastly, that the doubly symmetric wide flange members can be code checked. Basically, all the tapered sections can be analyzed, but those doubly symmetric wide flanged members can be code checked for different purposes. So with all of that, we can jump directly to S-frame. So here I have my S-frame already open. And the first thing that we are going to do is define a couple of characteristics or properties related to that tapered sections. So now I'm going to the section properties tool. I'm going to right click and open my section properties window and go into shapes. And here in shapes, we find the first approach about how we can start defining these taper properties. We have the properties at the start nodes and the end nodes. And here's the numerically approaching way to define these properties. I'm going to stick for the graphical ones, so we have it right here. But before that, make sure to select the tapered section type right here, so we can start working with the different sections at the end and the start nodes. So to get things or defined for the start node, I'm going to select an eye shape. And for this eye shape, I'm sticking for a wide flange for 200 millimeters, thickness of 30 millimeters, web depth of same 200 millimeters, thickness of 30 millimeters, 200 millimeters for the bottom flange, and for the web thickness, I'm sticking to 20 millimeters for this case. So click on OK. Going now for the end node, and when I open my shape, I can see that some of the properties, or basically all the properties, general geometrical properties, are retained. So I can easily define the new ones. I'm going to stick with the same thickness for each element, just changing the width and the depth of like this. So we have 300 millimeters for the flange width, butt and top and butt, and the bottom and the web depth is 450 millimeters. I click on OK. And now I'm going to define this as tapered section 1. Click on Add, and we have it right here. To select this color, and I'm going to close. So now I can define my member itself. And for that, I'm going to the member definition tool, and I'm going to, first of all, open my grid lines so I can have here a grid base to work with. And sticking for one joint because I'm aiming to create like a column. A member length of 5 meters. Everything is ready, so I can just click here and start defining some of these members. So I'm going to define two of them because I want to show about how that part of the averaging of the properties is working. So for now, I'm good with all of this. I'm getting rid of the grids and assign a fully fixed supports for both of these columns. I can jump to the loads windows. And here in the loads window, I'm going to define a couple of load cases. The first one will be a tip load. Okay, and the second one will be a member load. I can render this and see how this how are the properties graphically about the sections that I just defined. Can right click here and just get rid of the shrink factor so we can see the whole member. Now I'm going to define a couple of things. The first one being the tip load, going to stick for the join load in X direction. And this will be considered a positive, or rather inputting a positive tip load of 3 kilonewtons per 3 kilonewtons at the top of the columns. And then changing to the member load, I'm seeking for a global orientation in the X direction as well, so we can see how the member behaves under these circumstances. And I'm going to 1.5 kilonewtons per meter and assign it here and here. So with all of that, I can run my analysis, but before, let's get one step ahead. And going back to the geometry window, what I can do is just select one of the members. In this case, I'm going to unselect this one. And then going to edit and subdivide. And here on subdivide, what I'm intending to do is, first of all, not considering these average member subdivisions. I'm just going to input a 10 link property. I'm going to click on OK. And we can see now that our member got subdivided on that, following the characteristics that we input. If we render this, we can see now that the member is basically the same shape, but with different or less, or rather more quantity of pieces. And this will allow us to review with more accuracy about what's happening with our taper section. I need just to make sure that everything was input correctly. We can see that sectioning or subdivision get rid of my member load. I can just add it once more here. My tip load should be fine, and it's fine. And lastly, I'm going for the edit and load combination, and I'm going to include these loads or these load cases in the same load combination. That will be the first load combination for the tip load of a combination factor of 1, and the second load case being the member load with a combination factor of 1. Click on OK, and if I want to make sure that everything works just fine, I can go to the spreadsheet, change to the loads spreadsheet, toggle this or check this box, go to the combinations and see that the tip load and the member load are correctly defined here. So with all of that, I can just run my analysis. Okay, I want to save this and I'm going to change it Tapered sections, just like that. We don't have any kind of error. And the first thing that we can start drawing our attention is related to the deflection. So that's the first thing that I'm going to review. First, going to my load combination results right here. And then when activating or toggling on my deflection tool, I can see the resultant values and see that I have different values right in this occasion. We can see that for the first member that I define or we define, we are seeing a deflection of 1.20 millimeters, basically. I go here to properties to see a bit more detailed information. And this is because S-frame is averaging the properties or the section properties along of the member and basically taking like the midpoint between the start and the end nodes, and that's the section or the geometry that is considered. While here, when we segment or subdivide my element, I can see now that I'm receiving a more accurate results about how this element is reflecting. I can even activate and toggle this off and animate and see how things are working. And that could be the same when looking at the different diagrams. I can see that my shear diagram, I can see my moments diagram that won't present too much change. Can go to more stations and see that basically the shapes are the same, right? So right now we have two different ways of approaching this analysis and reviewing of my topper section. The first one goes with this linear definition that is basically following from one point to another and averaging my properties along the member. I have another option that is taking part or starting from our first approach, that is subdividing the member and even the shrink factor, just to see a bit more how things are being defined right here. That also creates a couple of different section properties that we have right here. And they basically distribute it in the geometry characteristics to achieve this behavior, this more accurate behavior. But we also have another approach, and that other approach may represent a more accurate way to see how those tapper sections are working. We can also decide to go for this approach since we can go for a more detailing way of seeing things, since we don't have a regular distribution of the loads and so on. And for that, what I'm going to do is first of all, getting rid of my selections and my rendering. I'm going to select my first element, Control plus C on my keyboard, and going for a clone multiple clone right here. I'm going to create another, let's say, tapper section or column section, tapper column section here. I have this part. So we have those three sections. If we analyze, we can see that the results from the first and the third one are practically the same. And then selecting all of this, what I need to do is going to this part. It says, when it says in the mesh, in the geometry window, to mesh, and it says convert members to meshable panels. At the moment I click here, I can see different kind of options. The first thing is that I want to get rid of this generate offsets at connection, so we can create the panels along the whole length of the member. And I'm going to check this box about convert joint connection only. And with all of that, I can click on OK. And we can see now that I have some panels defined right here. And these panels are considered as, if I'm not mistaken, yeah, those are shell mix mesh. I also have the same or the base member here defined or still defined. So I might want to get rid of that. I'm going to select this and unselect my panels. I can render just to see how things are being working right here. I'm going to get rid of this. And now everything that I have is this linear tapper section, this subdivided section, and these meshable panels going with the same shape of the first statement that we work with. So now it's just a matter of meshing those panels. So I'm going to this part. It says the panel element tool, just to make sure how the properties are being established so far. I can display the thickness and see that basically the thickness is going accordingly to what we define of the web and the flange thickness at the start of this quick lecture. And I can also work around the density or the mesh density, in case I'm interested in that. But since we unfortunately don't have too much time, I'm going to stick for this pre-default consideration that S-frame is inputted right here. And with all of that, it's just a matter of going to mesh and click here when it says mesh panels. Everything on the geometry window. Go to mesh panels. And I can see now that I have some mesh panels here. Just load them and see a render of that. I'm just need to make sure that all the loads are being input correctly. So to avoid try to add the loads one by one for the panels, I can go again to the geometry window and try to get rid. Well, the machine won't come up for this particular case, so I'm going to let loads. And what I'm going to do is going for this part, it says the uniform pressure tool. And this uniform pressure tool will help us to define that load for the shield elements that we have right here. So I'm going to go for the orientation of a projected or the local X values. And considering that we have a linear load for this of 1.5 kilonewtons per meter, and we have average thickness or sorry, web width or flange width of 0.25 millimeters. With just doing some calcs, I can conclude that the pressure that I need to input is of 6 kilonewtons per square meter. Just to add it right here. And I'm going to put my aerial view, hold my right click, my control, and draw this box to get rid of those loads. And now I can see that the pressure load is just assigned to this side of this flange. That is basically the same that we have if I go to the member load. And just before finishing, I'm going to add a couple of fully fixed supports to these joints. And with all of that, I can run my analysis. Okay, and we're not receiving any kind of message. That means that we define everything just fine. And then I can start reviewing what I have here. If I go again to the deflection tool, I can see that initially I have these values. And considering that now what I have input, I have a more deflected shape, and that goes with a more accurate representation of what we have. If we have a more, in a very quality mesh, we can also receive more accurate results. But right now we can see that it's presenting more deflections, so that we can consider that that's more accurate than the first approach or the second approach rather that we do with this subdivision. I can see the values related to the shield shear and membrane forces and review them on the different for different components. And it also extends to other values. In this case, since we don't have too much time, I can, or I take some images about some of the results that we are encountering. For example, here we have the shield contour results for that same element that we reviewed a moment ago. We can see that how the deflection is working, how the global moment is going for that shape, and also we have a global FXZ graphical representation of these results. So meshing some of those tapered sections can let us to understand a bit more about what's happening with them. And since there's no a regular shape along all the member, having the option of seeing this in so much detail could add a lot of value when looking and validating the results. And since unfortunately at the moment S-Frame can perform the code check to all of those taper sections, this could be a good way to make sure that our taper proposals for our projects are working just fine. That will be all for this lecture. Thank you so much for taking the time to attend this short webinar. Please stay tuned as we are going to present more of this about different topics, and let us know how you perceive all of this, and your feedback matters. So thank you so much.